So previously in the previous set of videos, we actually talked about the nomenclature and the definitions and equations of all your laminate that has a lot of plies. Alright, so this is one ply and then you stack with another ply, things like that. Okay, so we talk about all the definitions and equations for that. However, we didn't talk about the failures. What are the failure criteria? And therefore in this section we'll talk about the failure criteria and what are the equations to use in order to assess or to critique whether will the composite fail or not and things like that. Same thing, alright, there is a different methods of solving for isotropic materials and anisotropic materials. Okay, and therefore let's talk about isotropic materials first. Isotropic materials, in order to see whether your material or your composite will fail, you have to assess the von Mises stresses. Okay, and in order to do that, alright, you have to calculate your von Mises stress. Any stresses that is larger than your von Mises stress will fail. I repeat again, any stresses, alright, that is larger than your von Mises stresses will fail for isotropic materials. Alright, for materials that has same strength in all direction. Okay, so you use the von Mises stress. Okay, if you want to know more about von Mises stress, or you can go to my playlist, Sem 3 Mechanics 4N, type in von Mises and then search. Alright, and you should see a few videos and tutorial on von Mises and things like that. Or it's just a criteria to see whether will the material fail, and it's very much related to your use strength of your material. Alright, so this is for example your metal. Alright, this is strain, this is the stress. Okay, so this is the elastic Hooke's law. Alright, and over here this is the use strength. After the use strength it will deform, but however for composite it will not deform and therefore it will break. So the von Mises is somewhat like the yield strength, but yeah, never mind. You just need to know that this is the equation and that it can be simplified to a more simplified one. Okay, given that your stress in the x direction is much larger than the y direction. Okay, this is for analysis and design purposes. So you're trying to make things more simplified, so you can shorten the equation to an easier extent. Normally, if you want to because normally you want to compare whether isotropic material, what is the difference between isotropic material and anisotropic material. Okay, so I repeat again, you want to compare, alright, what is the largest strength, alright, it can be the material can take before fail. So you compare between isotropic and anisotropic. So normally the anisotropic is only one direction, which is the x direction. So isotropic, you want to also in order to compare with anisotropic material, you also want to take in the x direction, the strength of the x direction, and compare with the strength of the anisotropic material in the x direction also, to see what is the difference and to also see which type of material is advisable, alright, is or recommendable for use. Alright, so these are the things, and therefore for isotropic materials, you would actually minimize this equation to this one. Alright, taking that this one is very small. So if this one is very small, like 0.000 something, then you cancel off. Even multiply with sigma x is just also another 0.00 something, or less significant than this two. In other words, you just cancel these two lah. Okay, you'll get this thing. Okay, that's all. So you take this equation as your isotropic material equation for your von Mises. Alright, any value larger than this value or this thing sum up together, you will fail. So anything larger than these values will fail. That's it. Okay, and this is the stress, the strength in the x direction. This is the shear strength in the xy direction. And in order to calculate these two, okay, what you need to do is to come back to this equation, which we have discussed in the previous slide. Alright, if you just all the way go back, I don't know where, I think it should be this one, page 41, or around this region. Alright, it's very similar, but in this case we're only taking in the equations. Alright, so previously the stress in the one direction is this whole chunk. Because the stress y is neglected, so we can cancel off, we only have this one. Same thing for sigma 2, we take this one. Same thing for shearing, alright, we take this one. And therefore the simplified equation is this one. Okay, and this one is a transformation because you're transforming the xy direction to the 1, 2 direction. Alright, so the x and the y is this direction, the 1, 2 is this direction. So you are transforming in this angle theta. So this is why we have this angle over here. So once you transform already, you can find stress in the 1 direction, stress in the 2 direction, and shear strength in the 1, 2 direction. And then you compose inside the von Mises, and then in this equation, and then you see whether does the stress in the x direction larger than any of this. Or if it's fail, then it fail. Yeah. Or I repeat again. First step. Alright, calculate your stress 1, stress 2, and shear strength 1, 2. Given that if you have the stress in the xy and shearing direction, so you need to get information from here, information here, and then you transform. Alright, get this thing, then you take this thing and plug it inside. Plug inside where? Or plug inside here. Alright, the von Mises equation, and this is your von Mises strength. Anything larger than this value will fail. That's all. And this is for isotropic material. Hopefully this is very, very clear. Now let's zoom up a little and go to anisotropic material. Okay? And anisotropic material is the equation is slightly easier. Alright? So this is your strength of a material in the x direction. This is the strength of the material in the shear direction. Strength of the material in the y direction. And you need to know all these values. I think it's given from the manufacturer book or whatever. So you take it and then you divide by the angle theta. Alright? And then whatever stress that is larger than this thing, these values, will fail. I repeat again, whatever stresses over here, alright, this tree, alright, that is larger than either one of them, or in the particular direction, will fail. So I should say that this is in the x direction, this is in the y, this is in the s, this is in the y. So if the shear angle direction is the stress is larger than the shear strength, you will fail. Alright, so in the x direction, if the stress is larger than your x direction strength, then you will fail. That's all it is lah. Okay, and I may be wrong, so take note of it. Alright, and see whether in the future do you need to update or not. Alright, I may be wrong over in this, but it sounds logical now. Okay, method for solving for anisotropic material is called the Mec Stress Theory. Okay, maximum stress theory. Alright, what is the maximum stress for the x in the x direction, in the y direction, and the shear direction? So what is the maximum stress? So you calculate this, ensuring that no stresses is larger than them. Alright, if it's larger than these three values in their own individual direction, then you will fail. Alright, and this is the Mec Stress Theory. We have somewhat cleared away the understanding of a composite failure, and then stress strain against a certain angle, the shorter version, meaning the von Mises stresses for the isotropic material, and the Mec Stress Theory for the anisotropic material. Alright, so now we are left with two things. Alright, the TSAI HILL theory. So what is TSAI HILL theory? TSAI HILL theory is an extension of the Mec Stress Theory, okay, to a certain extent. The Mec Stress Theory is only for the x direction, in the shear direction, and in the y direction. For the TSAI HILL theory, is taking in direction from any other directions, x, y, and shear. Okay, it takes in same thing. Alright, it takes in the x direction, in the x direction, and in the y direction. Same. Alright, same consideration of Mec stress, but in the sense that it is kind of summing up them all together, ensuring that it is whenever if you have a certain addition, if you add them up together, ensure that they are smaller than 1. Alright, if it's larger than 1, then you will start to fail. Alright, so it gives you a prediction of when will you fail. So you can sum it all together, alright, and give you an overall result of when will it fail. Alright, and over here this one is for individually one. Alright, in the x, in the shear direction, in the y direction. So over here the Mec Stress Theory is more detailed. Alright, over here is give you the whole full picture of your whole laminate. Or your laminate includes all your plies already. Okay, includes all your ply. So in the Mec Stress Theory is in the x direction only, and in the y direction only, or in the shear strength, shear direction only. but for the SAI HILL one is adding up together to see in all directions, alright, what type of failure will it when will it fail. So SAI HILL theory is a more holistic one, alright, or more general one. For the Mec Stress Theory is more of a detailed one. Just take note of them, alright, ensuring that you should know both of them. So if you will compare the Mec Stress Theory, alright, which is this one, okay, this one, the Mec Stress Theory gives you a more detailed one, alright, tells you what is the failure mode and also the limit criteria, alright. So when is the limit for your x and in any directions, or in x, y, or shear directions. So what is the limit? For the SAI HILL theory, does not indicate when the failure mode, but will give you when will the failure initiate. Alright, will give you roughly the idea of when will the failure initiate. Alright, so Mec Stress Theory gives you the distinct limit, while I think SAI HILL theory gives you when will we initiate. Okay, hopefully this is pretty clear. So over here it says for UD composite. UD is actually a unidirectional composite, or in other words, an isotropic composite. Alright, meaning in a certain direction only. Alright, in this direction. Is a composite, alright, means that it can be stacked with other plies, but they are all unidirectional. Okay, and for unidirectional composite, that has uniaxial stresses, meaning in this direction, to the principal direction. The principal direction, I think it should be certain angle, at a certain angle. Okay, both will give same failure stress. Alright, so I think in a certain angle or not, they will give certain, I don't know whether there will be the both means this theory give you the same failure stress or whatever, for you to think about it, but it should not be quite important, I think. But you just need to know when will you use Mec Stress, when you use SAI HILL theory, that's all. In order to better view the maximum stress criterion and the SAI HILL criterion, alright, here is a graph, okay, to link them up together so you can see clearly. So over here, the scroll that I'm moving is actually for stress in the one direction, for the maximum stress. Alright, so what I've been telling you now is this one, the Mec Stress Theory, okay, where we talk about the different directions in the x direction. So now it's in the x direction, and then I also shift for the y direction. I shift a bit, and then for the shear direction I also shift over here. And if I were to plot the maximum stress in this graph now, alright, this axis over here is the angle, okay, while this thing over here is your ultimate strength or ultimate stress. Okay, so this one is the x, the y, and the shear direction. This is when you click this maximum stress, you should see something. Okay, so what do you see? Wait, give me a while. Yeah, so you see this type of curve coming out. So using the maximum stress theory, alright, the equations will sub in. The stress one over here, as you can see, is the black color line. Alright, with a certain angle, alright, then you have a certain high strength in that particular angle. Okay, and then over here, this is stress 2. So the higher the angle, the weaker you are. As you can see, as the angle moves towards this 90 degrees. So as you move, so for this one, if you move towards this angle, there is your fiber is acting in this direction, then your strength is going to be higher and higher. Eventually, if you think about it, it actually will move towards the 90 degrees thing. Alright, so in other words, the graph should look something like this. Okay, so because this is the transverse one, you actually go down. I repeat again. So the line that he's drawing, this is the angle. Alright, this is the thing. It's not an angle, but rather than fiber orientation. So if you have the one direction in stress in this direction, definitely it's kind of weak, right, over here. But so it tells you that if your stress 1 is in this direction, alright, like 0 degrees, okay, then you're going to talk about it is actually quite low for the stress 1. If you slowly increase the angle into this longitudinal one, then as you can see, if you're along this thing, your strength is quite high. It's going up all along. Hopefully you are kind of clear now. So over here, this is for stress 2. Stress 2 is over here in 0 direction. Alright, so in the 0 direction is quite high. Alright, it's quite high in this direction. But as you go downwards to the 90 degrees, as you can see, it is much weaker. Sorry, it should be the blue color one, sorry. But yeah, I don't want to confuse you. Yeah, I shall stop somewhere here. Alright, but I just need you to know that this is the graph. For the shear run, alright, at a particular angle, 45 is the somewhat the weakest. I don't know. Anyway, this is for the maximum stress criterion only. So what if the TSAI HILL criterion? What is it about? If I were to press the TSAI HILL one, okay, now blinking, you see, it is the area under the curve. Alright, give you the area under the curve. That is somewhere over here. You see? So whatever thing that is within this region, you are considered safe. If you're outside here, then you're considered unsafe. So this is the TSAI HILL criterion that is trying to say. That's all. For the maximum stress criterion, the graph is a bit chim. That's why I took quite a long time to discuss what the hell is it all about. Over here, this is a composite failure. Alright, we are still talking about composite failure, and it's actually over at this side. Alright, I should have said that here first. But anyway, yeah. So in order to let you see what are the different failure mode. Alright, so this is the website. Alright, you can click this link. Alright, and then if you were to talk about matrix deformations, meaning your resin deformations. So if I were to deform it, as you can see, when you pull the fiber, the resin actually move. Alright, and so for a tough matrix, alright, for ductile, normally you want your matrix to be ductile. Alright, so for a ductile matrix, alright, a high interfacial strength is desirable. Interfacial strength means that the bond between this thing, the fibers and the matrix, the yellow color one, this whole thing is all the matrix. Okay, it's desirable in order to favor matrix deformations. So once you deform, at least it's still strong. Alright. However, if it's a brittle so-called brittle matrix, alright, with a low interfacial strength, or it means that the bond between the fiber and the matrix is very low, then you can see crack, everything coming out. Alright, that's the meaning of that. If I were to reset the model and see what is the crack deflection, so if I were to load it, so as you can see, the crack is occurring at the top part. So stress field, as you can see, is coming out. Energy field. Wow, that's quite a lot of stuff already. Now I repeat again after reading. So I load this thing, you should see some crack coming out. Okay. You see the white line. This this white line over here. Alright, when you pull, there will be a crack. And this crack is talking about the von Mises crack. Alright, where if you think about it, the calculation that you have done for if it's an isotropic material, then it's using this equation. So anything larger than this one, they will crack. Otherwise, if it's an anisotropic material, alright, anything that is larger than your strength of the thing, it will crack. Alright, as you can see, it's cut to crack. Hopefully this is pretty clear. Alright, so once you crack, alright, there will be two theories to define your thing. So the first one is a stress field, alright, where it talks about the axial stress at crack tip, the red color one. So what it means over here is that the blue color one, the strength, is 20% of the strength in this direction. Okay, so the strength in this transverse direction is somewhat 20%. If in 20% of this direction, that's all. Okay, and it says that the crack will initiate, the crack will start to propagate, alright, if, alright, the strength of the bond between the fiber and the matrix, which is somewhere over here. So if the strength of this bond is also 20%, or less than, if the interface strength is less than 20% of the fiber strength. So if the fiber strength is, for example, 100%, so definitely 100% because of the strength of the fiber ma. So if the bond, alright, is weaker than the strength of the fiber by 20%, then it will start to propagate. Alright, you will also crack the fiber, I think. This is what it's trying to say. Alright, this is how why we're talking about this is because it's the behavior of the crack, how the crack will propagate for the composite. and what will initiate the crack is the bonding and the fiber and the stresses and everything. And then the energy approach is talking about if more on the energy release rate, I don't know what the hell, but it's talking about the bonding issue, alright, the more particle type of thing. Alright, so it's saying that if the interfacial bond, alright, exceed the critical energy, so the critical energy is actually the strength of the bond. So if the interfacial bond, I mean if the stress acting on the interfacial bond is big enough, alright, it will actually if it's bigger than the critical energy stress is larger than this interfacial bond, then it will break. Alright, things like that. Alright, hopefully this is pretty clear. This is for the energy field theory, and that's all for that. And if you click next, you will get to see that the crack will propagate. As the crack propagates, alright, you'll actually break the matrix. You see? You actually break the matrix, or the bond over here, fiber will start to fracture. Things like that. You can read yourself. I will not go through, I think it's quite deep already. But it's really a good website. And then if you were to go to void fiber pull out, then you'll start to pull the fiber out. As you can see, the whole thing will break. Alright, things like that. So this is how the whole composite failure initiate all along. And yeah, this it's really a very big topic. And this is what I click lah. I click this, and then eventually you'll get there. So in the next video, we'll talk about factor of safety. It's a very fast one. Alright, because this video is quite long already. So see you there.